All right, we're at 4:40, so we're going to power through our last part here. Okay, so advanced topics. So I've got 3 things, and then we had 2 more additions. Well, we had 3 more additions, and I'm going to smush one of them into my discussion of transverse modes. And then folks wanted to talk about combustor design and how you incorporate instability into combustor design. And I actually have some really good slides on that from my symposium plenary, so I'm just going to borrow from those. And then I will futz my way through a discussion of data-driven methods. And we'll see how that goes, because it's not something I currently do. All right, cool. Transverse modes. Buckle up, folks. This was my PhD, and I love talking about it. So far, a lot of what we've talked about is, I've mentioned these transverse modes, but we've mostly talked about longitudinal modes because those are kind of the easiest to think about from, if you learned acoustics yesterday. And so a longitudinal mode would be fluctuations that fluctuate in this direction, in this can combustor geometry, or in this direction, in this annular combustor geometry. And this is some work that was done in Thierry Poinceau's group. And this is a Helmholtz simulation, or a Helmholtz solver, that's plotting isobars of pressure. And so you can see there is like a longitudinal mode in this combustor. But then there's also a transverse mode. And one of the most interesting applications for transverse modes are in annular combustors, because if you do the calculation, you look at the frequency of the transverse mode and the frequency of the longitudinal mode, they're often very similar. You never want them to be the same. That's like really bad design. Don't do that. But they can often be on the same order. And so the mode that turns on, which is the, what we say in acoustics, that turns on first could be a transverse mode or a longitudinal mode, or, like in this picture, what's called a mixed mode. So this would be a T1L1, which is, actually this would be a T2L1, because you have a second order mode around here and a first order mode this way. Because both the circumference of this and the length of this are big numbers, the instability frequencies that you'd see in a typical engine are the order of hundreds of hertz. In a can combustor, the longitudinal mode is going to be on the order of hundreds of hertz. Any of the transverse modes are going to be on the order of thousands of hertz. And so they typically don't show up, but when they do, it's bad news, right? You just think about this from a high cycle fatigue perspective, right? You've got 1,000 pulses per second versus like 200 pulses per second. That's really problematic. And so they tend to be high amplitude and really hard to damp out. So these things not only stand still, but they spin, which is super, super fun. So this is, again, work from Thierry Poinceau's group. And this is the pressure wave spinning around. And this is the resultant, this is a temperature field. So you can see the cold reactants coming in, the hot flame, and then things downstream. And just really interesting. What I want you to watch, however, and this goes to some of the things related, and one of the reasons when I was a PhD student, I read a whole bunch of the liquid rocket engine instability literature. And liquid rocket engines, like we saw with the F1, the circumferential modes tend to be important. And one of the reasons that they're super important is because how this spinning mode, or even a standing mode, interacts with the injector. If you look in one of these injectors, right, if the color is pressure, you can see that the pressure in the injector is fluctuating wildly. This is called injector coupling. We're not very exciting about naming things, but you have an acoustic mode over the injector, and it talks to, through a couple different mechanisms, it talks to the acoustics of the injector itself. This is one of the main ways that instabilities are driven in rockets, because you have these super high amplitude pressure waves zooming around all these tiny little injectors. And when Tim and I started doing this work in grad school, when I was so I started my work in 2006, so this paper came a bit after we had published a bunch of stuff. you know, the same thing is happening in gas turbines. You can see the impact on the acoustics over here, but if you also just look at the motion of the flame, there are two different motions here. One is this sort of side-to-side wiggle, and that's, we'll see in a second, that's coming from the acoustic velocity fluctuation that occurs as a result of the pressure in the pressure fluctuation in the circumferential direction. But then you can also see there's a pulsing of this injector. And so it kind of barfs out material, and then, you know, there's a delay, and then it barfs out more material. And so you get this breathing or this coupling with the injector that's quite important for flame response. So these modes are fundamentally different in terms of how they interact with the flame as compared to longitudinal modes, just because of the shape of the acoustics, right? Like the thermoacoustic coupling process is the same. All our flame kinematics still work, but now instead of having, you know, acoustic fluctuations in the direction of flow, you have acoustic fluctuations normal to the direction of flow, and so stuff gets a little wonky when you do that. This is the diagram that explained my entire thesis. I highly recommend for PhD students to try and come up with like one picture that describes your entire thesis, and this was mine. This is a flow chart between the input and the output. And if you remember from the transfer functions we talked about before, this came from thinking about doing transfer functions. I tried to measure a transfer function, and there's a lot of issues defining like what's your reference velocity and where do you measure it, and is this even meaningful, and can you do this? And what part of the acoustic field is your flame at, and does it change the transfer function? There was a whole lot of disagreement at meetings and a lot of questions around it. So I said, why not just have all the transfer functions, not just one transfer function? I'll just turn everything into a transfer function. And went down a bit of a rabbit hole, but it was actually a really useful way of thinking about it. So the input to the whole problem is this transverse acoustic excitation, this mode that's spinning around, or standing. You can have standing modes. Standing modes, however, I don't have a good video of this. James Dawson does, but I couldn't find it online. I've just seen him present it at talks. If it's not spinning, sometimes it'll like very slowly just drift around, and which is kind of interesting. But unless you have some sort of symmetry breaking to hold the mode in one place, there's nothing in a symmetric system that tells it where to be. And so we'll see some data from his group that looks at spinning, the direction of spin, and some impacts on that. But you can get standing modes, but they tend to drift very slowly. In the experiment that I used, you'll see in just a second, we didn't have that problem. So we could dial things in pretty clearly. So, okay, what's happening here? So you have the input transverse acoustic excitation, and that can directly lead to flame response, depending on where you are in the acoustic mode, which we'll look at in just a second. That transverse excitation can excite flow instabilities. So this is your velocity coupling pathway. And the way that it does that is super interesting. And as a PhD student, I went down a big rabbit hole and wrote a couple like purely fluid mechanics papers on this, because non-axisymmetric forcing of flows with like swirl in them is super cool and really fascinating. And there's a lot of theory, and this coupling is not intuitive at all. And then you have this injector coupling, which is this FTL, right? So you have a transverse acoustic excitation, and just like we saw in the video from Poisot's group, you can excite longitudinal acoustics in the injector. And then once you have longitudinal acoustics, you have like everything else that you had before, right? So you can have longitudinal acoustics that affect flow instabilities. Both sources of velocity vortical velocity fluctuations can lead to flame response through a velocity coupling mechanism. So that's good. Longitudinal acoustics can talk to your fuel flow rate. We saw that before. So you can have equivalence ratio fluctuations that derive directly from the longitudinal acoustics. And depending on, you know, how your mixing is, it can also be influenced by your flow instabilities. And then you can have just the direct longitudinal forcing of the flame, like we saw with our pipe cleaners here. And all of these lead to flame response. And so a lot of my thesis was like pulling apart all these different things. I measured a lot of these things to understand what was going on. And it was a lot of fun. Like, I really enjoyed grad school and really was fascinated by this problem. And I was extremely lucky to be on a fellowship so I could kind of play around with stuff without having to answer to a sponsor and get creative with things and really press into a field that people hadn't thought about a lot. So this is my experiment. We took an annular combustor and we unwrapped it. This thing was 12 feet across. The window is a foot in wide, so you can imagine how big everything is. The experiment had racing stripes because all good experiments, all the experiments I've built have racing stripes. I don't know why, it's just a thing. But the flame sat in the middle. And then we had acoustic drivers. We buy police sirens. I have to get the university to send a letter, like she's not trying to steal a police car. This is for science, because citizens can't buy police equipment, which I think is a good thing. Anyway, we buy police sirens because they force really well in the frequencies we're interested in for gas turbine applications, and they're threaded, so you can thread it into parts really easily. And you can see all the wires everywhere. I did a lot of instrumentation. We could force one side differently than the other. The other things are these, we could tune it. So each of these slid in and out. So depending on the frequency, we could tune basically the length of the combustor to get a better acoustic resonance if we wanted to boost the amplitude of the signal. When these things were closed, 400 hertz really rocked in this experiment. And so if you read my papers, there's a lot of data at like 400, 800, and 1200 hertz because those mode shapes fit really well in the experiment. So here, we could dial in the acoustic mode shape over the combustor. And the very first thing I built was this plexiglass box with like a ton of ports for pressure transducers. It was the same size as this, and we were just making sure that this mode shape that we had predicted in acoustic modeling was actually going to work out. And it did, but for months, all I did was like one tone at a time measure the acoustic response of this plexiglass box, and everybody in the lab really hated me. And then they gave me an isolation room so that you can see actually the acoustic paneling on the walls that we were talking about before. So they put me in a room where nobody could hear me anymore, and that worked out much better. So we looked at this in two different ways. We basically looked at the extremes. We forced the two speakers in phase, so you created a pressure antinode, but a velocity node along the center line, right? So if you're pushing your acoustics this way, you have like a symmetry in the velocity, but you're compressing to a pressure antinode in the middle. And then we had out of phase forcing, and this was a pressure antinode, but a velocity, or sorry, a pressure node, but a velocity antinode, right? Because along the center line, you've got this big sloshing back and forth. And then we did a bunch of measurements. The response of the flow field, like I said, I did a lot on the fluid mechanics of swirling flows, which ended up being interesting. The flow generally responds with the symmetry that you force it at, although there's some interesting features of that. But what was super interesting was the flame. And so this is a pressure node, velocity antinode. So this is out of phase forcing. And what you can see from the video, this is just high speed. I didn't even have a filter on this. This is just luminescence forcing at 400 hertz. But you can see the flame, particularly at the base here, sort of wobbling back and forth. I tried to measure the stupid flame transfer function for this case for weeks, and I kept getting no response. I was like, is the PMT broken? What's going on? When I went to the pressure antinode, I got a response. So here, I'm forcing symmetrically. You have a whole lot of transverse to longitudinal coupling, and you get this really nice symmetric, nice ring vortex shedding on the flame. And I could measure a flame transfer function. And I was like, what gives? So let's use our pipe cleaners to think about what gives, right? What's happening in the bottom case where I'm forcing symmetrically, I'm getting wrinkles that are symmetric on the flame, right? And so all the things that are happening on one side of the flame are reinforcing all the things that are happening on the other side of the flame. And so they're just adding together, and globally you're getting a big response. But when you force transversely, they're canceling each other out. And so this is why I was getting no global response. Like, you look at this video and this flame's like really moving. It was very loud in there. I get my hearing checked every year because I'm like very nervous about all the sound that I subjected myself to as a graduate student. But I saw no global flame response. It was all just noise. And it's because what one half of the flame was doing, the other half of the flame was canceling out. We didn't really, like, we guessed that may have been what was happening. But then I had a partner, a theoretical partner. His name was Vishal Acharya. He's still a research scientist at Georgia Tech. And he did all the level set for this situation with the swirling flow and transverse forcing or whatever. And he got 0 global response. And I was like, whew, all right. So theory shows us, and we could see the base wave and the local wave and all this jazz put together. And we could see why the response was 0. And that was a huge relief. So I didn't look like such a clown to my advisor that I couldn't measure flame response for half of my thesis. So this is quite important. But this was just one flame. We then did it with 5 flames, which is kind of fun. But then James did this with lots of flames. And so this is the experiment that we saw before. And here they're changing 2 things. They're changing the number of injectors. There's 12 up here and 18 down here. And then they're changing basically the spacing between them. They're also changing the swirl number. So you can see these flames are a lot more symmetric than these. And that's because the amount of swirl here is much higher than it is here. And so they wanted to see what the spacing versus the swirl number ended up doing to the mode shapes. And these plots are beautiful. So what these are, here, let me put my pointer back. I was so happy when he started publishing this work. It was after I had finished my PhD, but it really put a lot of this stuff into context. So he's got a ton of pressure transducers around this thing, and so he can measure, just like we talked about with the multi-microphone method in the longitudinal case, he can measure the spinning modes using multiple microphones. So he can measure the clockwise spinning wave and the anti-clockwise spinning wave and calculate its amplitude. And he and Nick put bounds on it, right? They looked at, this is a probability density function of the amplitudes over they just let this run for a long time. And sometimes the mode was in the middle, right? If these two are equal-ish, then they cancel each other out and it turns into a standing wave. If one is significantly higher amplitude than the other, it's spinning anti-clockwise here and spinning clockwise here. They're British, so they say anti-clockwise, not counterclockwise. And so you could see as you changed the spacing and the swirl number, so everything here is swirling together. Here, they didn't change the swirl number, they changed the direction of swirl. So one swirl clockwise, one anti-clockwise, one clockwise, one anti-clockwise, right? And it dramatically changed how the mode, the acoustic mode, the thermoacoustic mode, would stand in the combustor. When you balanced out the alternating swirl, you just got everything to stand. But when you had everything swirling in the same direction for a bunch of different spacings, you could get these asymmetries in the system, which was absolutely fascinating. Highly recommend, all the work that Nick and James did together on this experiment was just gorgeous. And they have beautiful visualizations. And if you really want to get a feel for transverse instabilities on a system level scale, their work is really nice. So just a quick note, going back, because somebody had asked about well, what about rockets? rockets have the same situation. This diagram explains rockets as well as gas turbines. And the name of the game is really FTL. And so I wrote, I think it was a national meeting paper, where we measured this. And then a colleague of mine did a lot of acoustic modeling to understand the impact of injector design, particularly the acoustic impedance. This problem is an acoustics problem that then turns into a flame problem. But you got to do a lot of really good acoustic characterization on your system to be able to understand this well. And so this is the main mode of instability in rockets are these transverse, both circumferential and radial modes. And so how those waves talk to the acoustics inside the injectors are really controlling the amplitude of the instability. And so if you're clever about your injector design, both from a fluid mechanics standpoint, but also an acoustic standpoint, you can really help with that. Okay, so transverse instabilities. Second thing, nonlinear instability. So here I'm not talking about nonlinear flame response. We already talked about that, right? We talked about kinematic restoration and cusp forming and all that kind of stuff. No. I'm talking about nonlinear instability. So what do I mean? This is a linearly unstable system because if I start at an instability amplitude of 0 and I add a disturbance of epsilon of infinitesimally small amplitude, the instability will grow. And that's the definition of a linearly unstable system. You can think about a ball on the top of a tippy top of a pointy hill, and any little disturbance, that ball's going to roll down the hill. So that's a linearly unstable system. A nonlinearly unstable system looks like this. At infinitesimally small disturbances, nothing happens. Driving is less than damping. But if you kick it with a finite amplitude disturbance, you can trigger the instability. So remember I admonished myself earlier for using the word trigger. This is why. Triggering in instability literature means something very specific. It is kicking a nonlinearly unstable system hard enough that you get an instability. And that process is called triggering. So now, in a nonlinearly unstable system, you have two important amplitudes. You have the limit cycle amplitude, which eventually you get to, but you have the triggering amplitude, which is the amplitude you need to kick the system at in order for you to get growth. So there are some really good examples of this. The first one is the Space Shuttle booster rocket. When they were testing this, they knew solid propellant, solid rockets are famous for nonlinear instability in truly epic ways. And so what they would do when they were testing these things is they would light it, and then they had like charges, like little explosives in the, not little, they're big, right? It's a friggin' space shuttle. They'd have these charges where they blasted them to try to kick it into instability. And so you can see in this test, they light it, and like this is, you know, just things being loud, right? Combustion's loud. And they hit pulse 1, and you can see the system oscillates, and then it goes back down, right? So what's happening there is pulse 1 was probably like here, right? So a stable system, it'll still oscillate, just like we saw with those fluid systems before, but then it dampens itself out. But then pulse 2, boy howdy, that really did work. And you get these absolutely massive instabilities. And the growth is really rapid, and you get, you know, very destructive behaviors. And so one of the things that this is important for, you know, you're not going to put charges in an actual rocket engine. That's a terrible idea. But one of the things that can happen to solid propellants is like chunks come off. And when the chunk comes off and gets into, they're usually monopropellants, right? So it's not like you're waiting for some interface between oxidizer and fuel. It's all together. So when that chunk comes off and then gets entrained into the hot products, it kind of explodes. And so that can be a trigger for an instability. And they wanted to understand how high amplitude that trigger needs to be so that they could like make sure that chunks weren't going to come off that big to cause this to happen, because this just tears the system apart. You can see these amplitudes, thousands of PSI, peak to peak, which is bonkers. This doesn't happen a lot in gas turbines, thank God. But there was a paper that was written by Kyute Kim, who's now a professor at KAIST, and Simone Hochgreb at Cambridge. Kyute was a postdoc in her group, where they saw this happen in a gas turbine, or a model gas turbine combustor. And so this is a cool paper because it's kind of rare to see this. And they did a really nice job. They did such a nice job, they actually measured this driving curve, which is very, very impressive. And so this was like the cherry on the cake. But if you look, what they would do is they'd light it. And so you light it with a spark igniter. And if you kind of half-ass the spark igniter, then you just get, kind of unstable combustion. But if you really punched it from the same operating condition beforehand, you could trigger it into a full instability. Which is pretty neat. And so they probably found this accidentally. A lot of good science is found accidentally. And then really did a nice job characterizing it. And so if you want to see a very thorough study of triggering and nonlinear instability, this is a good application. So nonlinear instability is really the name of the game in solid rockets. In liquid rockets, it happens a bit, but those can be linearly unstable. And in gas turbines, they're mostly linearly unstable, except for a couple cool situations like this. OK, next is entropy coupling, or what is sometimes referred to as indirect noise. Direct combustion noise is just combustion's loud. Right? It's turbulent. You've got some thermoacoustics. Like, you've just got noise. Entropy coupling is called indirect noise because it's the noise from the interaction of entropy at boundary conditions, which is pretty interesting. So this goes back to Chu and Kvasny. Again, we return to Chu and Kvasny all the time because it is a very, very useful formulation. And so entropy coupling is a unique instability because, like I said, it requires the interaction at a boundary condition. So this is a combustor, right? So fuel and air come in here. This is a flame. And then you have some choke boundary condition or close to choke boundary condition at the back end. In this case, a lot of people are looking at this for gas turbines, particularly because this happens often. You'll hear this instability referred to as rumble. It happens on startup of engines a lot when stuff's really cold. And then once everything warms up, it just goes to regular thermoacoustics. But if we look at how this works, so let's say you kick the flame and you get a heat release rate perturbation that leads to an entropy oscillation, right? We said our modes of perturbations are acoustic, vortical, and entropic. And entropic oscillations are dilative, but not rotational. OK. I'm starting to lose my voice, guys. All right. This blob of hot, high entropy fluid convects downstream at some convection velocity. And then it runs into the boundary condition. One thing Chu and Kvasny hints at, but doesn't talk about, there's a separate paper that talks about it, is what these coupling mechanisms look like. There's linear coupling between these different modes at boundary conditions. We said there's no coupling in free space. But when you get to a boundary condition, like we saw with acoustic damping, you can get linear coupling between acoustic and vortical disturbances. Here, when you send an entropic disturbance and it hits a hard boundary condition, or an acoustically hard boundary condition, which is what a sonic throat is, which is what you got in the turbine, it sends back an acoustic wave. So now you have this convective disturbance moving downstream. When it runs into that nozzle, it creates an acoustic disturbance that propagates back. Can't propagate forward because it's sonic in there. So the turbine doesn't know this is happening. But you send that acoustic wave back, And now you can imagine if you've just sent an acoustic wave back to the flame, that acoustic disturbance can drive another entropy disturbance through heat release rate oscillations, and this can all happen over and over and over. So this is the coupling process. The frequency at which this happens, though, is not in acoustic mode of the system, because an acoustic mode requires like acoustic propagation back and forth, and here you have convective propagation in one direction and acoustic propagation in the other direction. And so instead, in order to calculate the frequency at which this happens, it's going to be 1 over the period, tau, because that's the definition of frequency. And so then you got to think about your two time delays. So there's the convective piece and the acoustic piece. And so you can calculate these, right? The convective piece is the length of the combustor over that convective velocity, and the acoustic piece is the length of the combustor over the speed of sound. This is a long time. This is a short time. Long time plus short time, 1 divided by that is going to be a pretty low frequency, which is why we call this rumble, right? It's typically on the order of tens of hertz. So low frequency, but sometimes you can hear it. And if you're on an airplane when this is happening, you get a little bit freaked out because you don't want low frequency tones coming from your engine. And so there's a lot of really good work happening in a bunch of different places, both theory and experiment, looking at indirect combustion noise. So there have been, like I said, a lot of examples of this. I haven't shown a ton of CFD results, and so I will do that now. It's just not my jam. But from Thierry Poinceau's group, they did a really nice study. They just get as many computers in France as they can hook together and just do really nice LES with a Helmholtz solver so they can get the acoustic modes. Thierry gave a really excellent symposium plenary in South Korea whenever we had that meeting, maybe 2016. Was that the meeting in Seoul? I forget. It's online. It's absolutely worth watching. He talks about simulation of thermoacoustic instabilities, which is very computationally intensive. And it's just a great talk. And so highly, highly recommend. Anyway, this is work he did related to indirect combustion noise. So this is just a sector. He's got the whole annulus. And you got the swirler. And then you've got this choke nozzle. And so he's looking at the process. This is a temperature field. So you can see pretty standard RQL type combustor configuration. So you got a hot flame here, big dilution jets, and then burnout. And then they looked at a pressure probe here near that sonic nozzle to understand the acoustic waves that were being generated. So they did, I think it was a dynamic mode decomposition. I think it was DMD, some sort of decomposition. I think it was DMD. Anyway, this is the spectrum at that location A. So you see these nice pointy things, and that's the instability. And then when they looked at the dynamic mode decomposition, you can really nicely see, these this convecting temperature. This is temperature blobs that move downstream, interact with the nozzle, and create this instability. So this paper, I think, does a nice job showing this visually, where in experiments it's very hard to do because measuring temperature fields is very difficult. So this was a cool contribution. But like I said, there's a lot of really good experimental work happening on this and some good theory. And so particularly lately, I'd say in the past 6 to 8 years, a lot more interest in this particular issue. OK, so the last two things that folks had suggested, and we can, if we have time, we can just keep calling them out. But I know we also have posters to do. The first is combustor design and instability. So I've warned you all about how bad instability is. But what do you do? Like, how do you avoid it? And so let's talk about how you design combustors and then how you might avoid this problem when you design it. So I'm stealing these slides from my plenary talk at the symposium 2 years ago. That's also online. It deals a lot more with the hydrodynamics. So I talk a lot more about flow instability and what that means for thermoacoustics. And so if any of this was interesting, feel free to watch that. I'm actually pretty proud of how that talk turned out. So, and I'm glad that that's a reference. There's also a review paper that goes with it. But the talk had a shruggy emoji, which the paper does not. Okay, so, but this was the end of the talk. And so we did all this stuff talking about thermoacoustics. And then I said, okay, well, what does this mean for design? So the way we design combustors, and again, this came from a paper written by Håkan Mangia, who was really, a design guru at GE Aircraft Engines or Aviation, whatever they called themselves. Now it's GE Aerospace, for decades. And is, his fingerprints are on a lot of very high quality combustor design as a result. This is kind of the current combustor design methodology. So you typically start with the design you have now. There are very few clean sheet combustor designs because that feels like a lot of effort. The first thing that you do is you make modifications and you look at what they do in design tools. And there are a ton of design tools. There are tools to look at flow splits and pressure drops. And, we haven't even gotten to RANs. These are just like basic, analytical flow solvers or, structural solvers or things like that. Correlations. There's a set of correlations. You can find it in Lefebvre's book on dilution jet trajectories. He just did a bunch of curve fitting from a ton of data and was like, yeah, this sounds about right. And then, you got the old guy who nobody will let retire. And he's a design tool in and of himself, right? So there's all this sort of first cut knowledge that goes into getting a pretty good shape based on what you think it should look like. Then you put it into CFD. 10 years ago, I would have said this is mostly RANs with a couple very fancy special LES cases to double check the RANs. That's no longer the case. We're running a lot more LES on combustor systems now just because computing power has gotten better and industry has invested in computers. And national infrastructure for computing has gotten better, right? So people can apply for time on DOE computers and get it, and industry absolutely does this. There's much more LES that's happening to refine things. Then you take this and you rig test it. And, this was pretty cheap. This is some money. This is a lot of money, right? Because now you got to cast a part, or now you 3D print it, which is fun. So a lot of fuel injectors are 3D printed, even for production. GE 3D prints some of their fuel injectors for production. But a ton, basically everybody now, if you just want to put out a design quickly, because you can print pretty easily in things like Inconel and Hastelloy-X, which are pretty common nickel-based superalloys that you use for these things, and get a pretty good part. So then you put it in the rig, and you just beat it up, right? You measure flame transfer functions, you do tons of operability testing, you change a lot of things, and you really put this thing through its paces. Rig testing, you do a single cup, and then you have a sector rig, and then some companies have annular rigs. And then once you're really confident, you put it in a test engine, you say your prayers, and you really hope that everything you did so far works. And then you put the test engine through its paces, and you go from there. Instability issues tend to come up in rig testing. More and more, we're finding them in CFD because we're doing higher fidelity. You can't find it in RANs. Right? Equations don't allow you. I guess you could in URANs, but it's a little janky. But you can see it in CFD, but it's really hard. Coupling LES with a Helmholtz solver is not trivial. Again, watch Poinceau's lecture for how not trivial it is. And so still, we mostly find these in rig testing. And that's what rig testing's for, and it's fine. If you find the instability there, you go back to the beginning and you fix it, right? And it's not terrible. It's not awesome, but it's not terrible. What's really bad is if you don't catch it in rig testing and you find it in engine testing. Because now you've put all this hardware, you've made multiple of these injectors, you've put all this hardware in an engine, and now it's quite expensive. And if it's really bad, it could damage other parts of the engine. This test engine instrumented to the hilt, so you're probably burning up instrumentation that nobody wanted you to burn up. The turbine guys are really mad at you because they had other goals for the engine tests, and now it's too loud and they've got hot spots, and you burnt off a bunch of their instrumentation and they're not super happy with you. And so it's really bad, but it's way better than finding the instability when you install the engine, which still happens and nobody's happy about. But this still happens, which is why we put dampers on engines so that we can avoid this problem. Yeah?
You spoke about there are many design tools available.
They're all in, there's no like, for combustor design, I don't think there are any like commercial tools. These are all homegrown, like correlations, flow solvers, like, again, documentation from old guy who discovered some magical formula in 1986 and it still works. You know, like, this is the internal knowledge of companies that they really don't like to talk about.
It's not open source.
No. You should find the old guys, though. Hookham was one of them. You know, before he retired, I had a lot of great conversations with him, just like war stories about design. But yeah, like, these are all homegrown tools based on experience. So they're not commercial. Okay, so hopefully, you're not finding your instability in an engine test, and really hopefully you're not finding it at a customer site, because that's super bad. So that's basically how it fits in. Typically, you're scanning for thermoacoustic instability now in CFD. And again, Poinceau's lecture talks about that. And so so I've just got a list of names of people who do really good work in both thermoacoustic modeling tools, so like these network tools. So, you know, Amy Morgan's name is on there. Both Stowe and Morgans were students of Dowling's. But Thomas Sadelmeyer, Wolfgang Polifka, Bruno Stroman, Nicholas Norre, Mirko Botheim, Matthew Juniper, Jonas Moek. There are a bunch of these folks who, some of them are just theoreticians and computational, some of them are theoreticians and experimentalists, but they're putting together you know, these kinds of first-order models that help you see thermoacoustic instability before you get to the CFD. And then you've got the Poinceaus and the, what's his name? Furby at, where is he? Somewhere in Northern Europe. I should know this. There are a bunch of people doing really nice high-fidelity LES to be able to predict thermoacoustic instability. And then the rest of us laser jocks doing it in rigs. So now there are a lot of tools. One of the points that I was making in my plenary was that we should also be looking at the hydrodynamic instability. And Matthew's been, you know, beating this drum for years, Matthew Juniper, with little success. But we'll see. I think there's some stuff catching on. But anyway, this is basically where you would see it in the design process. And people are definitely thinking about this. One of the things that I really like about this community is more than half the names up here worked in industry for a while. So Thomas, Wolfgang, Bruno just came to academia. He was at Alstom and then GE for a long time. Nicolas and Mirko, again, Mirko just made the jump. Jonas, and so they have the experience on and are bringing it back to academia from the industrial side, which for a problem like this, yes, the theory is so important, but it's very device specific, right? I made that joke at the beginning. This is job security, because every single engine's going to look different, and it's all going to have its own special problems. But because so much of this is geometry dependent, you really got to understand the technology in addition to the kinematics in order to put everything together. And so if this is an area you're interested in, you know, pick your technology, rockets, gas turbines, you know, industrial systems, and then just learn a lot about that too. Okay, The final thing I'll say, any other questions on that? This is the thing I feel I can speak authoritatively about. The last topic, I cannot. So I'll say a couple things and then ask for some final questions. Okay, so somebody asked about data-driven methods. You know, data science is so hot right now, and everybody's trying to do it. There are some people who I think are doing it gracefully. Actually, probably the work that I'm the biggest fan of is Matthew Juniper's work, and there are some others as well. But one of the biggest opportunities, I think, goes back to this point that I made before about what a pain in the tail it is to either model or to measure flame transfer functions. And so I had showed a picture from Nick Bunce's thesis. Where is it? Here we go. This plot took Nick years, right, of taking data, analyzing data, realizing half of it was bad, retaking it, doing the uncertainty quantification, you know, and gaining insight from it. But it just takes a long time to measure a lot of these things. It takes a very long time to simulate these things. My colleague Yuan Schwan's doing a lot of good work in simulating, trying to do transfer function simulations. Wolfgang Polifica's group has done some really creative work in this area as well. And it's just really difficult to get all the details, right? This theory gives you a first cut, and it gives you a gut intuition for what the disturbance mechanisms are. But for real engine, this isn't going to cut it, right? If you want like the real turbulent response, you either got to measure it or you got to simulate it, and both things take a long time. And so I know some of the work that Matthew's doing and others, my academic sibling Santosh Chandra is looking at this as well, is how do we use data-driven methods to help us, you know, fill in the spaces either between certain measurements or certain simulations to cover a wider range of operating conditions so that we can faithfully predict thermoacoustic instability over the whole operating map and not have to measure everything, or measure some stuff and then cross your fingers and hope it works in other places. So from an opportunity standpoint, that's where I see the biggest opportunities. This is not my area at all. I'm very lucky to be friends with some of the people who are doing this kind of work, but it's not work I'm doing, so I don't want to say anything that's wrong. I just hope there are other very smart people who are going to figure this out so that my students can stop measuring transfer functions. Okay, and with that, we have a couple more minutes. I'd be very happy to answer questions or stick around afterwards, but I want to say thank you. You guys asked a ton of good questions. It was a real honor to come back as the first summer school alum to teach one of the courses. And so I'm glad you were on this journey with me. Hopefully this was helpful and interesting and kind of fun that we did crafts. If you want to learn more about what my group does, that's our website. I will be here tonight and up through lunch tomorrow. So if you want to talk, I'm around. So thanks, team.